Okay, welcome everyone. Today we are very happy to have Shota Komatsu from CERN, and is going to tell us about Einstein gravity from matrix integral. Over to you, Shota.
Okay, all right. Thank you very much for the invitation, and I'm happy to give this seminar. So yes, today I'm going to talk about my recent works. Together with these people. Which we wrote like last year. There are two papers, and it's in collaboration with basically three people in EPFL, Joe Penedones, you probably know, and then there are two students, these two people, well, and also Shan, who used to be a postdoc at EPFL and who is a postdoc now in Sac Lake. And then those three people basically did a lot of work of heavy computations of supergravity and supersymmetric localization. I should also mention that the same model that I'm going to talk about was also studied in a paper by Sean Hartnell and his student Jun Liu, which appeared around the same time, but we kind of explored the different aspects of it. Okay, so before starting to explain the content of the talk or the details, technical details, let me just give you the punchlines. So the punchline is the following. So we made some proposal between duality, in the sense of holographic duality, between mass deformed IKKT matrix integral. So which is, I'm going to explain what that is, but it's basically just some kind of matrix integral, with 10 bosonic matrices and 16 fermionic matrices. And the duality is between this matrix integral and certain type 2B background with certain supersymmetry. And this supergravity background is basically given by some kind of a two-dimensional manifold over which S2 and S6 are fibered. Okay, and the methods that we used in order to propose or verify the validity of this proposal are basically the supersymmetric localization of matrix integral. And that's what we did on the matrix model side. And then on the supergravity side, we constructed the BPS supergravity solution explicitly. And one of the punchline one of the outcome is that each saddle point of the matrix integral seems to correspond to different supergravity solution that you can construct. And I should also mention that similar analysis were already done in different model, what's called BMN matrix quantum mechanics, which is the mass deformed BFSS quantum mechanics. And in that context, a localization of the matrix quantum mechanics was done in this paper, whereas the supergravity solution was constructed in this paper by Lynn Madasena.
So, sorry, Shota, to interrupt you so early, but will you be working with Euclidean signature or Minkowski signature?
I will be working with Euclidean signature, yes. Yeah, okay. That's one important point.
Thank you. Thank you.
And so the more concrete evidence that we're going to show is that the saddle point equation of this matrix integral after doing the localization actually corresponds. So this saddle point equation, like in the usual large N matrices, is given by some integral equation. And that integral equation also shows up as a data characterizing this supergravity solution. That's basically the punchline of the talk. Okay. So with that said, let's proceed. So this is the plan of the talk. So I will first give a review of IKKT and also briefly review the BFSS in order to give some context about why we are studying this model. And also I introduce a mass deformation of the IKKT model. And after that, I will explain the matrix model side, which is supersymmetric localization, and then talk about the gravity side, which is a construction of the supergravity solution, and then end with discussion and conclusion. Okay. So let's start with the IKKT and mass deformation. So the model that I'm going to talk about already Sandeep asked. So the model is called a Euclidean IKKT matrix model. So the model was first intensively studied. Well, first studied by this paper, Ishibashi-Kawai-Kitazawa-Tsuchiya. So that's why we call it IKKT matrix model. And This is basically some theory of n times n matrices. So these xi's are all n times n matrices, which has 16 supersymmetry and SO10 symmetry. So these i's runs from 1 to 10, and then there is a SO10 symmetry. So here I'm talking about Euclidean, what's called Euclidean version, in which the symmetry is SO10. There is a similar, different version, which is called Lorentzian IKKT matrix model, in which the symmetry is SO1. But in this talk, I'm going to focus on Euclidean version. And so as you can see, like this takes a form of like an action of super Yang-Mills theory in general dimensions. And in fact, like this action arises from a dimensional reduction of, for example, 10D n equals 1 super Yang-Mills down to 0 dimension. And you can also think of it as a low energy effective action of the D instantons, so D-1 branes. And in the original IKKT paper, they mostly focus on Lorentzian version rather than Euclidean version. And then they propose that this Lorentzian version gives some kind of non-perturbative definition of type 2B superstring. So this is slightly different from like a usual ADS-CFT correspondence, and it's more in the spirit of it's more in the spirit of what's called like a BFSS conjecture, which conjectures that certain limit of the BFSS matrix model describes the non-perturbative 11D M theory. Well, I'm going to explain that in a couple of slides. Okay, but I should mention that so this this proposal as a non-perturbative definition of type 2B string, its status is even less clear than the BFSS conjecture, which by itself is less established as compared to the standard ADS-CFT holography. And so to explain that point, so let's briefly review what is the BFSS conjecture. So in the context, the BFSS conjecture is about what's called BFSS matrix quantum mechanics, which is basically like a analog of IKKT model, but like in 0+1 dimension. So here we have time direction. And then this is a matrix quantum mechanics with 16 supersymmetry and SO9 SO9 bosonic symmetry. And similarly as the IKKT model, this describes the low energy dynamics of D0 branes. And the interesting property of this model is that if you look at this part, which you can think of as a potential term of the matrix quantum mechanics, you see that classically this matrix quantum mechanics has a flat direction because if you take all the matrices to be diagonal, then like there is no potential. And normally when you have the flat direction in matrix quantum mechanics, you would expect that basically all the states are like a scattering states, and then only delta function normalizable, like in quantum mechanics on a line without any potential. However, unusual feature of this model is that it's understood that like this has actually unique normalizable ground state. By normalizable, it actually means that it's like a Kronecker delta normalizable. And in addition, this ground state, this matrix model also has a continuum of multi-particle states. And so these multi-particle states, the interesting thing about this BFSS model is that these continuum of multi-particle states are also described in some sense using the normalizable ground state. So let me explain what that means. So the idea is that you first consider like n times n matrices, and then divide it into say like a smaller diagonal matrix of size n1 and size n2. And then you put some ground state wave function, which is basically normalizable ground state wave function of the smaller size BFSS matrix quantum mechanics. And you do the same on this side. And after that, you give some like a relative momenta of these two blocks. And then, so of course, like nothing is fully like under analytical control, but it is believed that if you construct states in this way, then it is believed that it describes some kind of like a two particle states in which like and the size of n1 or like a size of n1 eigenvalues form some kind of bound state here, and then the other set of eigenvalues form another set of eigenvalue, and then because of the relative momentum in the 9 direction, it basically like a scatter with each other. And the conjecture is that if you consider such scattering states or multi-particle states, and then take appropriate limit, large N limit, together with certain strong coupling limit. So you also need to send R to infinity, where R appears as a coupling constant here. Then it is given by some 11D M series flat space M series scattering amplitudes. Yeah, in which like a momentum is yes.
What is ABFSS?
So ABFSS here is a quantum mechanical scattering amplitudes. So this is a quantum mechanics, but like much like in quantum mechanics with scattering states, you can define the scattering amplitudes.
Okay.
And this P1 is just like the momentum in the 9 direction. And then the idea is that eventually this N1 over R, this ratio, becomes the momentum in the light cone direction. So, and of course, like so you also need to determine P plus, but P plus is just determined by the on-shell condition. So like this is supposed to be described in the scattering amplitudes in 11D of supergravitons. Okay.
So just to make sure, so the notion of, so as you explained, there is a precise notion of one normalizable ground state, and then there is a precise notion of these continuum of multi-particle states, I gather. So the idea is that your P1 and P2, these two blocks asymptotically become some kind of, two asymptotic states, scattering-like states in the mid.
Right. Yes. That's the basic idea. And of course, we don't know, we cannot write down this normalizable ground state. Like there are many evidence coming from index computation, or like in the case of SU2, there are more direct evidence based on more detailed analysis that there is a normalizable ground state, but the details of the normalizable ground state wave function is not fully understood. However, like we believe that people believe that this is like a general physical picture. So you can also think of this as a part of the conjecture. The existence of the scatter, like this kind of scattering state, is technically speaking part of the conjecture.
Okay, thank you.
Sorry, Shota, remedial question. So the total P minus should be 0, right, for the scattering?
That's true, yeah.
And I see that the P minus on the right hand side is a positive quantity.
Okay, sorry. Yes, so here I only wrote the in state, but of course in the quantum mechanics, like if you scatter these blobs, like these like a bunch of eigenvalues, there should be some out state. So what you are going to compare is really like a physical scattering amplitudes, like in the physical kinematics with bunch of in state and bunch of out states on the BFSS side, and also you do the same for the 11D side. Okay. So this is a very like ambitious conjecture, but there are like several kind of justification. I put the justification in the quotation mark because I think like none of these argument is like as solid as the argument that leads to ADS-CFT, which is technically speaking by itself a conjecture. But one justification comes from the following proposal. So here in this formula, you are taking large infinite and limit, and then the conjecture is that gives you the flat space 11D S matrix. But so one way to justify this is to kind of like a step back a little bit and then discuss the finite and BFSS. And so the slogan here is that like so this was discussed in these papers, but the slogan here is that the finite N BFSS corresponds to what's called like a DLCQ of M theory. So DLCQ stands for discrete light quantization. And what it means is that instead of like, if you consider finite N BFSS, instead of getting the infinite space, like a flat space M theory, you instead get some M theory in which the light cone direction is compactified. So let me just briefly review the argument. So the argument goes as follows. So let's start from this side, right-hand side. So let's start with the light compactified 11D M theory with radius R. And this light compactification is oftentimes not fully understood. So in order to have a better picture of what that is, it's useful to make the circle slightly space-like, like so, like this. Okay, to make it well-defined. And once you make the circle slightly space-like, you can boost it back and you can make it really like a spatial circle. But because it was almost light-like, this spatial circle is very small. So now, after doing this procedure, DLCQ of M theory gets mapped to some M theory on a spatial circle, but with a very tiny circle. And we know that if you compactify M theory on a tiny circle, we expect that it reduced to 2A. So in some sense, like this, so well, this is a kind of one way to argue that the light compactified 11D M theory is well described by type 2A string theory. However, so if you carefully track, so what you really want to do is to kind of like study the finite energy state in this light compactified frame. And if you carefully track how this finite energy state translates in the type 2A picture, you find that this light compactified DLCQ does not really correspond to generic type 2A superstring, but it corresponds to a certain limit of the type 2A string, in which the string coupling goes to 0, whereas alpha prime goes to 0 as well, because yeah, the string scale also goes to infinity. So if you require that the state you want to consider is a finite energy and finite Planck scale in DLCQ, then it turns out that it corresponds to a certain limit, which turned out to be exactly the same as the decoupling limit of the D0 brane in type 2A. By which I mean like it's some limit in which G string goes to 0, but alpha prime also goes to 0, but the Yang-Mills coupling constant on the D0 brane remains finite. And if you take that limit, basically the closed string decouples from the open string on D0 brane, and also you can the massive open string on D0 brane also decouples because it becomes infinitely heavy. And in the end, the theory on the D0 brane just becomes like a Lorentz effective theory of D0 brane, which is BFSS matrix quantum mechanics without any stringy corrections. So
sorry, Shota. So could I just put it like this, that in light of the ADS CFT conjecture, or rather it's D0 brane analog, if I believe that, I take the Maldacena limit for 0 branes, I get some 2B supergravity background, which has a curvature scale, the analog RADS for ADS 5. And now, starting from that, I take n to go to infinity, and I land up in the infinite matrix size limit of the matrix. And basically, if I've done it right, I end up in flat at least 2A of some kind, maybe somehow M theory. Can I think of it like that? Like given the Maldacena limit to justify the BFSS? Okay, I mean you can.
Yeah, so that's right. That's probably like the second thing that I'm going to talk about in the next slide.
Okay, sorry.
Yeah, so at least like as far as I understand, like this BFSS conjecture is now justified by the combination of the two logic. And the first logic is this one, which is about actually finite and BFSS. So which is slightly different, which is kind of different from the Maldacena limit. So okay, so let me go to that part. So slide was about finite and BFSS, and then the conjecture was that that should know something about DLC of M theory rather than flat space M theory. And then in the original papers, they are discussing that, okay, so now we know what is the finite a light compactified M theory. So we can just send R to infinity where R is the size of the light cone circle. And then we can recover the flat space M theory. So however, this argument is a little bit too quick because R is actually the length on the light circle. So the proper length of the circle is always 0. So physically, it's a little bit suspicious to say that R going to infinity just recovers the flat space. And this part, to understand this second part, the R going to infinity limit, people later kind of use the connection to the ADS-CFT correspondence. So that's the part Sandeep was probably asking, which is discussed in this paper. So if I were to explain it in one sentence, the slogan is that the back reaction makes the light circle space-like. So in this paper, they basically analyze the usual holographic dual of BFSS matrix quantum mechanics, much like how people study the holographic dual of N equals 4 supermills, which is then ADS5 times S5. And so they wrote down the type 2A geometry, dual to BFSS matrix quantum mechanics, and you can also uplift it to M theory. And in particular, if you look at that geometry, especially uplifted to M theory, then you see that when R, which is the a radial direction, goes to infinity, so which is kind of near boundary limit in the context of ADS-CFT, you see that M series circle becomes light-like, which means that the proper length of the M series circle is very, very small. However, at the core, at R equals 0, you see that this M series circle becomes space-like and very large. So pictorially, the geometry that you get is something like this. So in the far R going to infinity region, you get 11D, but compactified on a very tiny proper length. So you can think of it as 10D type 2A. Whereas in the middle, you get 11D, a flat space-like region. So now, combining the two pictures, we expect the following to happen if you take appropriate N going to infinity, R going to infinity limit. So if you consider the scattering of these blobs of eigenvalues, then each of these blobs basically back reacts the geometry, and in the middle, you have 11D geometry. So this is these are gray regions. Whereas outside, exterior is given by 10D type 2A regime. And then when they scatter, and when they meet at a point and they scatter, you get a large 11D flat space region. And if the scattering, if the main effect of the scattering happens in this 11D region, you would expect that you can kind of extract the 11D S matrix. But of course, this argument is very far from a proof. For example, this only explains that there is some relation to 11D S matrix, but the BFSS conjecture is a very precise relation between scattering amplitudes in quantum mechanics and scattering amplitudes in 11D theory, and it doesn't really justify that precise relation. And then that's why it's a far from proof, and then it's less established than the decoupling limit of the usual ADS-CFT correspondence. And however, yes.
Usual ADS-CFT type logic, one would have expected the thing that would be dual to the scattering amplitude is some sort of a correlation function.
Yeah.
Trace operators.
Right.
So this seems like a different object than that, where you stack up the things and then scatter the stacks.
Yeah, exactly. Yeah, that's quite different, I think. So in the usual flat, for example, also in the ADS-CFT correspondence, you can take the flat space limit, but in that case, you basically first construct some ADS5 times S5 geometry, and then study correlation function, which is small perturbation, and then try to extract the flat space region. But here, the story is very different.
So if one were to do the other thing where these correlation functions, would that be would that be interesting object from the bulk point of view, port bulk from point of view?
Yeah, I think that's an interesting object. So far, I think the flat space limit of ADS-CFT was really discussed only in the case of like a conformal theory, like n equals positive Mills or like ABGM. So here, like the DO geometry is like is sorry, the BFSS matrix quantum mechanics is not conformal field theory. So the DO geometry has more features, and I think it's interesting to try to understand how to extract really the flat space limit in the usual sense of ADS-CFT.
Okay, thank you.
And so, however, I should say that like so this argument actually combines the two, and then the second part is really holographic duality. So the holographic duality BFSS certainly gave us some good physical intuition into what's happening, especially why we can possibly recover the flat 11D spacetime. Okay, so now the natural question you can ask is, what about IKKT? Okay, and so, however, like as compared to BFSS, like there haven't been so many works on holography for IKKT in the past. Although there are several important works, so let me just review like two important works, both one on the matrix model side and the other on the gravity side. So on the matrix model side, especially in this paper by Moore, Nekrasov, and Shota, they computed the exact partition function using supersymmetric localization. And the result is given by this expression. So this is a kind of complicated function of n, but what I want to highlight is the sigma 2 part, which is called the divisor function. So this is a sum over all possible integer which divides n, okay? And the important point of this divisor function is that it depends strongly on the number theoretic property of n. For example, if n is prime number, you only have two sums, like 1 and n itself. And whereas like if n is 2 times prime number, you have more sums. And this result for the IKKT, so let me also make a comment that this result for IKKT partition function was also used in a recent paper by Ashok in computing the instanton correction to 4 graviton scattering amplitudes in type 2B string theory. And then he verified the conjecture coming from S-duality by Green and his collaborators. So this was just a side comment, but the more important thing that I want to highlight is that because of this divisor function, if you, for example, plot this divisor function as a function of n, it doesn't actually have a smooth large n limit. It oscillates of order 1, like in an interval of order 1. So in some sense, it's kind of erratic in n.
So this is partition function being computed for the BFSS?
So the part for the BFSS, right? So you can so this IKKT partition function, you can also think of it as an index of BFSS partition function. So that's something that was computed.
This is like the K-theoretic versus homological.
Okay. I'm not that familiar with that.
Okay.
So I guess.
Sorry, Shota, very sorry. Just to understand, by Z IKKT, we just mean the matrix integral, right?
Right. Yeah, this is matrix integral.
Yes. And it gives a finite answer, I guess, and this is it. Yeah.
Right.
Okay.
Is the style like this Nekrasov partition function, instanton partition function? Is that how one computes this?
Well, they do use localization, but I think it's probably slightly different because like this is basically just a full answer. Well, okay, so you get some matrix integral and then you evaluate it. Yeah, I don't know what you mean by Nekrasov partition function, but certainly like the integrand is much simpler than Nekrasov partition function.
Thank you.
Okay, so now let's move on to the gravity side. So on the gravity side, right after people discussed ADS-CFT, it was natural to also consider, people are discussing like a DP brane geometry, and then it was natural to take p equal -1 to understand the dual of the like a d instantons. So this was discussed by these papers, and in particular, decoupling limit was discussed by this paper by Auger and Iskanderis. And so the gravity side is rather simple. So in the Einstein frame, the metric is just given by just a flat metric. So, and whereas there is a non-trivial profile of the dilaton, which depends on the radial direction. And however, like if you go to a string frame, because of the non-trivial profile of dilaton, the string frame metric is non-trivial. And furthermore, it has an interesting property that this metric in the string frame has R going to 1 over R symmetry. So because of this, like if you look at the string frame metric, there are actually two asymptotic flat region. Like one is R going to infinity, and the other is R going to 0. And because of this, like they called it wormhole geometry. And so and then if you want to take a decoupling limit, much like Maudasena's argument that leads to ADS-CFT, the natural thing to do is to drop this 1. So this is what we normally do for the DP brane geometry. So that's what was discussed in Auger-Iskanderis. And if you do that, then you basically kill the R going to infinity regime, and then you just focus on R going to 0 regime. Okay, so however, there are several conceptual subtleties in taking the decoupling limit of this D instantons. So the firstly, normally, like in the usual ADS-CFT argument, excitations, so when you take the near horizon limit, on the geometry side, you focus on the excitation near the throat region. And in the one argues that that corresponds to some low energy modes of the D brane. So that leads to some kind of like a simplified the correspondence between simplified geometry and some low energy excitation on the D brane. However, in this context of the D instanton, first of all, the gravity size is just flat. So especially in the Einstein frame, so it seems there's no redshift. And similarly, on the matrix model side, because the matrix model is just matrix integral, there is no clear notion of time or energy. And so it's a bit unclear what we really mean by the energy scale, like taking the low energy limit. And what is worse, as I already mentioned, like the IKKT partition function doesn't have a smooth large N limit, which is a little bit puzzling from the point of view of the gravity, because on the gravity side, at least like there is no obvious reason why like a large N expansion, which is a genus expansion of the type 2B string theory, needs to break down at some point. And so this basically means that either there is something very subtle on the gravity side, which leads to non-smooth like a genus expansion, or maybe the correspondence is actually not really correct for this model. So that motivates us to look for some better setup for studying holography. Okay, so what is the better setup? And the better setup that we would like to propose is that the better setup is actually the mass deformed IKKT matrix model, which we also call it polarized IKKT matrix model, following the terminology introduced by Hartnell. So one thing I should mention is that actually this model itself was written by Bonelli 20 years ago in one of his papers in the appendix. But because the model was in the appendix of some paper whose main theme is kind of like about a different topic, so not many people actually realized that there is such a, well, not many people knew that there is such a theory. So this model is basically just the IKKT plus some mass deformation. And then you also need to add some terms in order to preserve supersymmetry. And because of the mass deformation, the original SO10 bosonic symmetry gets broken down to SO3 times SO7. And furthermore, one thing I should emphasize is that it has 16 supersymmetry, which is exactly the same as IKKT matrix model. And this 16 supersymmetry in SO3 times SO7 symmetry actually combines into what's called exceptional F4 Lie superalgebra. So I guess not many people are familiar with this Lie superalgebra, but let me just mention that this is a unique superconformal group that can exist in 5 dimensions. So in 5 dimensions, in the context of 5D superconformal field theory, this SO7 needs to be replaced by SO5 comma 2. And so in that sense, like what appears in this model is a different real form of this exceptional Lie superalgebra. But this is a kind of interesting fact is that this is actually a unique superconformal group that exists in 5D. So the situation is quite different from 4D or 6D, in which you can have several different superconformal groups. And another, was there any question? Maybe not.
No.
So another important point is that unlike the original IKKT model, which I mentioned that it doesn't have smooth large-n limit, so this model does have smooth T-Foote expansion, standard T-Foote expansion, standard large-n expansion. That's basically because of this mass term, which gives some propagator to the matrices. So you can just run the usual argument of double line notation and then classify the diagrams using the 2D Riemann surfaces. Okay, so another important fact about this model is that, yes?
So why is it that you like this particular symmetry breaking pattern? And why is it that only this admits this T-Foote expansion?
Okay, so yes, that's a good question. So it's not fully proven, but I think if you insist on like turning on mass deformation to every direction, like all the direction, like 10 directions, and then you also insist on having 16 supersymmetry, I believe this is the unique choice. So for example, like already, like you can ask some like a mathematical Lie superalgebra question. What is the SOP times SO10 minus P? So what is the Lie superalgebra which contains SOP times SO10 minus P with 16 fermionic generator? And I think the answer to that is unique, and it's given by this exceptional F4 Lie superalgebra. So if you allow yourself to break more SUSY, I think there are more possibilities.
I see.
Okay, so this is, and another important property of this model is that if you solve the classical equation of motion of this model, you find that the classical vacua are given by what's called fuzzy sphere. So the classical vacua needs to satisfy this equation. So I use the word vacua, but it's really just a saddle point or the classical saddle point because we don't have time. And so the equation motion sets like a x1 to 3 to satisfy this equation, which is often called the fuzzy sphere solution, and then it sets all the others to be 0. And the general solution of this fuzzy sphere solution is given by this kind of expression. So as you can see, like this is the same as commutation relation of SU2. So you basically choose some SU2 representation of size n1, and then it can have several, and then you put them diagonally. And the same representation can appear several times. So this small n1 is basically the multiplicity of each representation. And so if you classify all possible choices of such like SU2 representation, then you can convince yourself that all the possibilities are basically given by all the possibilities of partitions of n, which means that the number of vacua in this theory is equal to the number of partitions of n.
Sorry,
Okay.
how are these numbers related to capital N? Nk times Nk is equal, sum over that is N, or just small nk sum is equal to N?
Capital Nk times small nk summed over k is equal to n.
Okay.
Yeah, thanks for the question. Okay, so with that said, let's go to the analysis of the matrix model. So this is a kind of like a basically technical analysis. So we just follow what we did is to just follow the strategy of like a supersymmetric localization done by Moore, Nekrasov, and Shotashvili, and which is to use that supersymmetric localization. So we follow the strategy and I computed the partition function using supersymmetric localization. So the basic idea is to deform the action by some Q exact term. And because it's Q exact, it doesn't really change the value of the partition function. And then you can send this parameter t to be infinity. And in that limit, you can compute it by saddle point plus one loop fluctuation. And then that gives the exact answer. And you can choose this deforming action in such a way that the localization saddle basically corresponds to this classical vacua. But there is a small difference. So in this localization saddle, x1 to 3 basically takes the same form. So again, like there are like a partition of n different localization saddles, and x4 and x9 are set to 0. However, x10, there is some freedom. So x10, the only constraint that we get from localization is that x10 needs to commute with x1 to 3. And the general structure of the matrix which commutes with x1 to 3 is given by this expression. So you have identity matrix on the first side, on this like a first term, whereas like this MIs can be arbitrary. But these MIs mutually commute because it lives on the different diagonal components. So you can just diagonalize these MIs and then reduce it to eigenvalue integrals. So the upshot is that, so you have partition of n different localization saddles, and around each saddles, there is some like a flat direction parameterized by MIs, and you need to do this matrix integral around each saddle. However, like this is much simpler because original matrix simpler than the original IKKT partition function, because in the original IKKT partition function, you had 10 non-commuting matrices, but here we only have like integrals over the commuting matrices plus the sum over saddle points. Okay. And after all the dust settles, we get this expression. So the partition function is given by sum over all possible saddles, which is given by the partitions of n. And for each partition, you get this matrix integral. So it has a little bit complicated form. So let me explain to you the structure. So because we have different kinds of matrices which live on the different diagonal components, so we have like a different species of eigenvalues. So these different species are labeled by like this parenthesis S here. But the potential part of this matrix integral is just Gaussian, whereas like this interaction part, which in the usual Hermitian matrix, you just get a van der Monde factor, but that is now more complicated. It depends on like which species you're talking about. And basically like all these like species interact with each other through this kind of a little bit complicated expression. So it is complicated, but it's still a rational function. Okay. And so although it's a complicated expression, we can still use the usual large N matrix eigenvalue technique. Basically, like you introduce the density of eigenvalues and then write down the saddle point equation. And so if you do that, you get a following equation from the saddle point equation. So so the details of the structure doesn't really matter, but like this non-trivial factor comes from this non-trivial, like a generalized van der Monde factor. And also like because we have several species of eigenvalues, we need to introduce several different eigenvalue density. Okay, so this is a kind of like what replaces the standard large M saddle point equation. So okay, so this is the end of the matrix model side analysis, and now I'm going to explain how one can recover this equation from the gravity side.
Hi, I have a question. Yeah, so when you
Yes.
say you are doing this large and this saddle point approximation, that ns is very large than 1. So you
Yeah.
mean all of these matrices M1, M2, MQ are very large.
Right, exactly, yeah.
And how are you justified in doing this analysis that so ns will be fixed, this sum, when I'm doing large N analysis, this sum of ns is fixed to be capital N.
Mm-hmm.
So how are we justified those partition where one of the matrices is small, let's say M1 is of order 5 or 6, and rest of the matrices are very large? Like, won't they?
Okay, yes, that's a very good question. So here, like what we are aiming, like I'm not claiming that this is the dominant contribution of the full partition function. It seems like there is a more microscopic holography, like in the sense like for each saddle point, there seem to be some holographic deal. And as for some of those saddle point, like the holographic deal may not be described well by the supergravity, but for these for these saddle point, there is some smooth geometry, and then you can recover this equation from gravity side as well.
Okay, thanks.
Hi, Shota.
Yes.
Yeah, I have a question. So you said that for each of these saddles you have these flat directions, right?
Mm-hmm.
Will that not diverge the integral?
Oh, yeah, sorry, the terminology, sorry, the flat was a bit misleading. Yes, sorry for that. So what I really meant is that there is some like an integral that you need to do around each saddle point, which is given by these MIs. But as you can see, that MIs comes with a Gaussian factor, so the integral does not really diverge.
Okay.
Which is what you expect because we did the mass deformation.
And this last expression is for a given P, right?
For given P, yes, yeah.
But as you integrate, sometimes two eigenvalues can coincide, giving you a bigger block.
Right. That is true, but here like xi's are like already fixed, so so there is no kind of interaction between different saddles.
Mm-hmm.
So you can use like these x1 to 3 to distinguish different saddles.
Yes. Okay. Okay, thank you.
Okay. Yeah, so but before going to the supergravity side, let me just mention one surprise, which we don't, well, we know how it happens mathematically, but we don't have a quite physical understanding of this. So one surprise is that, so we studied a mass deformed IKKT matrix model, and the natural expectation is that like, if you take this answer for the mass deformed IKKT and send omega to 0, you should recover the IKKT matrix model partition function. Well, at least like at the level of the Lagrangian, it's true. Like if you take mass deformed Lagrangian and take the limit, you get the IKKT Lagrangian. However, it turns out that's not the case. So if you take the mass deformed partition function and send omega to 0, it actually diverges like omega to -2n. Whereas like if you directly compute IKKT partition function, it gives a finite answer given by sigma 2. Well, this is mathematically not, well, this was a bit of surprise initially for us as well, but mathematically this is not a contradiction because oftentimes doing the integral and then taking the limit actually do not commute, and then you can clearly see that that's one of such cases. But furthermore, what's more surprising is that on the polarized IKKT mass deformed IKKT matrix model side, we have some integral which is of this form and with a bunch of poles in the complex plane. So instead of doing the integral honestly on the real axis, if you deform the contour by adding a contour at infinity and then evaluate this localization integral using the residues on the upper half plane, and then that gives a different answer from the one in which you do the integral on the real axis, because there is like this contour at infinity actually does not decay. But the surprising thing is that this different answer, if you take omega to 0 limit, correctly reproduce is finite and correctly reproduces IKKT partition function. So this is something we found. We don't quite know what is the physical meaning.
So do you actually get this sigma 2 of n from this?
Right. Yeah, so that's actually surprising. Like, yes. So you get an expression which contains sigma 2 of n.
I see.
So yeah, this might be a bit interesting also mathematically, like to understand how this divisor function shows up. So what we did is actually, we only did for the case by case, like n equals 2, n equals 3, n equals 4. So we don't actually have a general proof.
Oh,
Shota, is it related to the fact that IKKT to begin with had these flat directions? At least if you think naively, because you know, and now, I mean, it's to begin with already a bit surprising that the IKKT partition function turned out to be finite. But when you give the mass deformation, it's a sort of different order of limits. You sort of lift the flat directions first with omega. It seems somehow connected to this, how you're regulating the flat directions in some way. Sorry for the vague comment.
I agree. Yes. Yeah. More technical, at a more technical level, IKKT partition function is finite because like integrating out fermion gives you some sufficient like a power law decay in R, but that like a power law decay in R gets modified if you do the mass deformation. Yeah, that's the only another comment I can make, and then I don't really have much insight about this, but I agree what you said.
Okay, thank you.
Okay, so now let's talk about the gravity side briefly. So this gravity side analysis, I'm not, well, already on the localization side, I was not giving you a lot of details, but on the gravity side, I will give less details because okay, so it's a kind of highly technical subject. But let me just mention that we didn't do the computation from scratch. So we actually made use of the fact that this exceptional F4 Lie superalgebra, which governs the IKKT, mass deformed IKKT matrix model, appears in different contexts, which is in the 5D superconformal field theory. So fortunately, like a BPS supergravity solution dual to 5D superconformal field theory, preserving this exceptional F4 supersymmetry, have been constructed in a series of papers by the UCLA group and also this paper by Nunes and his collaborator. And of course, like as I said, the real form of the algebra that appears in our context is different from their context because in their case, they had like a SO5,1, but we have SO7. However, the local analysis of the constructing a supergravity solution is the same. So we can basically take their results and then like appropriately impose a reality condition and like a global consistency condition. So such analysis basically leads to the following geometry, so which is given by this kind of geometry. So you have like S2 and S6, whose size depends on this rho and z, which is additional two-dimensional plane. And furthermore, if you require the BPS condition and also the smoothness of the geometry, you find that this S6 needs to shrink on this z-axis, whereas like S2 needs to shrink on the rho axis. And by the way, like a geometry lives on this like this quadrant. And in addition, you can also we find that we can also put some slits, which is horizontal and then parallel to rho axis, on which S2 also shrinks. And so this is a bit complicated geometry, but let me just say that because S2 shrinks on these blue slits, so if you draw this line, so this actually gives you some kind of like a 3 cycle, like the endpoint is given by, so this is S2 times interval, And at the end of the interval, like S2 smoothly shrinks, so you can have like a smooth compact 3 cycle. And similarly, you can have like 7 cycles. And on these cycles, like there are non-trivial fluxes, and then you have like a D1 and NS5 and then D5 charges. Okay. And in the another interesting property of this geometry is that when you move far away in this Z and rho direction, it basically approaches the metric of Auger-Skenderis with constant C2 flux. Well, this flat metric of Auger-Skenderis plus some fluxes. Yes.
Where are these brains coming from?
Oh, the brains. You mean the charges?
Yeah, because you just had a D-1 brains to begin with, right?
Right. So I think like it should come from something like a Myers effect, in which like the instanton like puff up into D1, for instance.
Yeah, the D1s one could think of like that you have this fuzzy two sphere, as you say, and there's
yeah, D1 you can think of it as fuzzy two sphere indeed.
Yeah, the 5 brains is more strange, right? Isn't it, or what?
Yeah, 5 brains, it's hard to see from the matrix model side. So yeah, right. Let me just say that the same thing is supposed to happen in the mass deformation of BFSS matrix model, which is often called the BMN matrix model. So also there can be like a D2 charges and D4 charges. And I think D2 is easy to see because again, because of the fuzzy sphere. But D4 is harder to see, and it's supposed to be non-perturbative. But recently there are more evidence coming from supersymmetric localization that the BMN matrix model knows about D4 brain as well. So,
just to understand these brains, these 5 brain, whatever, they wrap a non-trivial cycle so that there's actual D5 brain charge, or is it that?
So here, like it's fully geometric. So it's like when I say D1, NS5, D5 charges, it just means that there are fluxes corresponding to these brains.
Fluxes.
So in this geometry, everything is geometrized.
Okay. Thank you.
Okay, and so another important point is that so all these like H and R2 and R6, they are like 3 non-trivial functions, which all depends on like this rho and Z. But although there are like 3 non-trivial functions, but all of them are determined by a single function, which I denote V, and then this function V satisfies a simple linear differential equation, which turned out to be the same as equation for the 4D electrostatic problem. So this is just a Laplace equation written in some axisymmetric coordinates. So these axis, and then rho is basically some like a radial direction, and it satisfies this equation. Yes.
Yeah, how do you get this equation? Is it from Einstein's equations?
Yeah, so you impose the Einstein and BPS. Well, I think here like supersymmetry is stronger, so you impose a BPS equation, the supersymmetry. But you can also check that like with this, when this is satisfied, and when you write everything in terms of V, you can this satisfies the supergravity equation of motion. Yeah, so the relation is not very direct. For example, in the first paper in which they analyzed 5D superconformal field theory, they didn't realize that there was electrostatic description, and it was only realized later in this paper when they rewrote the solution they got. And another thing is that like because you also need to impose the boundary condition. For example, S2 needs to shrink on these blue lines, and the metric is always smooth. And this imposes some boundary condition to this electrostatic potential, which basically means that like this V, which basically says that V needs to be constant along these blue lines. So you can think of them as conducting balls in the context of electrostatic problem. And in addition, there is some background potential, which comes from the positivity of the metric. So I'm a bit behind. I'm already running out of time. So, but let me just give you a brief explanation of the correspondence with the matrix model side. So the correspondence seems to work in the following way. So on the matrix model side, we have this kind of vacua. And basically the size of the representation, capital N, corresponds to the height of conducting balls, whereas the multiplicity, small n, corresponds to the charge of the conducting ball.
Shota,
Yep.
sorry, just to let you know that we are flexible with time. So
Okay. Yeah, but okay. Thank you for that. So, but anyway, like I only have like 2 or 3 more slides, I guess. But so the correspondence with that is that like a size corresponds to the height, and the charge the multiplicity corresponds to the charge of the conducting ball. And then in the string theory language, this height corresponds to NS5 charge, and then this charge corresponds to D1 charge. So this second part is like is in line with what Sandeep and other people said, that like this fuzzy sphere basically corresponds to D1. So if you have more fuzzy sphere, then it means that you have more D1s. And so there are certain limiting cases which are worth to be mentioned. For example, if you have just one disk very high in the z direction, that basically corresponds to spherical probe D1 brane. So especially like when this disk has only unit charge, we expect that it doesn't, well, it's actually, technically speaking, it's not really described by some smooth geometry, but it's more described by some D1 brane, probe D1 brane placed on some geometry. And the other limiting case is you only have like one very large, just a small representation, but very large multiplicity. For example, if you consider the trivial vacuum in which like this is all just identity, then it should correspond to this kind of picture. And that is supposed to be dual to some probe NS5 brane. So according to this dictionary. So that one is actually harder to see because on the matrix model side, the saddle point is just like a trivial saddle point. Okay, so let me and then let me just give you a bit more concrete correspondence, especially explain how to recover the integral equation that I showed on the matrix model side from the localization, from the gravity. So basically the integral equation arises from the requirement that the potential V that you compute from these like conducting balls needs to be constant on each ball. So the idea is that like solving the 4D Laplace equation, you can express the V as a sum over contribution from each balls, right? Because like a Laplace equation is just linear and the electrostatic problem is a linear problem. So you can express the potential at arbitrary point as a kind of functional of the charge density on each ball. But this charge density cannot be arbitrary because when this potential reaches, when this point reaches this like a conducting ball, it needs to be some constant value. So it shouldn't vary on the conducting ball. So that leads to this kind of equation. So you basically, so the total contribution of the potential needs to be some constant on each ball. And so the background contribution plus the contribution from each ball needs to sum up to constant, okay? And in this equation, I already wrote it in the form that you can compare with the matrix model side. And the point is that this equation is exactly the same as the matrix model saddle point equation. The only difference is that here, this rho has an interpretation as the charge density of the electrostatic problem, whereas in the matrix model side, rho has an interpretation as an eigenvalue density. Okay. So this gives you some precise agreement with the saddle point equation of the supersymmetric localization. Okay. So let me just summarize, and in particular, like because I started talking by the undeformed IKKT, so let me just give some comparison with the undeformed IKKT. So in summary, it seems like in many ways, this mass deformed IKKT is better behaved than the original IKKT. For example, as I said, original IKKT doesn't have smooth large N limit, and the gravity duo is not fully understood, whereas the standard large mass deformed IKKT has standard large N expansion. So we expect that it's due to some string theory background. And on this side, you can also construct a supergravity solution, and then you can also do some quantitative match with the gravity side. Although like there are several mysteries like taking the massless limit. Okay. All right, so let's conclude. So the conclusion is that we propose the duality between polarized IKKT matrix model and type 2B supergravity backgrounds. And the main method we used was the supersymmetric localization, which expresses the partition function as a sum over partitions, sum over saddle points, and for each saddle point, you get a matrix integral. And the main outcome of the analysis is that the saddle point equation of the matrix model side is equal to the data characterizing supergravity solution. And I should also mention that there are some loose ends which we didn't really analyze, or more precisely, we didn't manage to analyze in the paper. So one important open question, which we didn't manage to do in the paper, is to evaluate the onshore supergravity action. So on the matrix model side, we have a matrix integral, so we can also evaluate the saddle point action coming from each saddle point. So it'll be nice to also evaluate the onshore supergravity action on this background, and then try to compare or try to match it with the localization answer. However, this turned out to be a little bit complicated because this is a non-trivial, non-compact geometry, and then determining the precise boundary term at infinity is a bit non-trivial here. So normally, if the geometry is like asymptotically ADS, people more or less know how to determine the boundary term, preserving supersymmetry. But here, the geometry is not asymptotically ADS, so it's a little bit tricky. And another thing that we didn't do was to this observation that the residue contribution gives you IKKT, but we only did it for case by case for fixed N, and it'll be nice to give a general proof. And lastly, in the context of 5D superconformal field theory, people also constructed solutions in the supergravity in which there are some D7 branch charges on the geometry side. And it'll be interesting to construct the supergravity to generalize their analysis to our case, and also try to understand what it means on the matrix model side. And there are also like a more ambitious and interesting question, like building a holographic dictionary. And we also have like a results for localization correlation functions. We wrote it in the paper, but we didn't kind of analyze the physical meaning of them. And another interesting question is to whether we can do the matrix model bootstrap studied by these people in other contexts. One difficulty is that the measure is not positive by itself. So one needs to invent some trick. The measure of IKKT path integral is not positive. And most interesting question may be to understand whether there is any implication to the original IKKT conjecture, which says that Lorentzian IKKT in certain large N limit gives a non-perturbative definition of type 2B string in flat space. Okay, so let's end here. Thanks a lot.
Questions?
Shota, just towards your last point, let me just understand. So suppose I take a very simple solution, which is one fuzzy two sphere. You know,
Mm-hmm.
so all the n branes are in one fuzzy two sphere, some big fuzzy sphere. That presumably corresponds to now some particular Sugra solution where you have, I wasn't able to do it in my head, but there's some map where n enters as some parameter of the curvature or something on the supergravity side. And then is there any sort of suggestive way of taking n going to infinity on both sides to say that, you know, you might be landing on something like a flat limit of 2b? Or is that not a sensible question?
I understand your question. So I guess like so firstly, I think the situation we are talking about is basically this, I think.
Yeah, that's what I'm thinking. That seemed the most promising to me. Maybe I'm wrong. Like just one irreducible representation. Then you have, yeah, that's what I was thinking. But, you know, maybe I'm wrong. But because then you have a map to gravity of just this one parameter. And can you take a large n limit on both sides and see what happens? Or
right, that's interesting question. But in general, like so I think like okay. So one possible way of getting the flat space is, as you said, like take some solution and then take some limit, and at the same time take deformation parameter to be 0 as well, and in a nice way, and then try to hope to get some flat space region. But if you try to do it, like a different region of the space-time behave differently, like as you would expect, like the region near the slit behaves different from like a region in the middle as you take the limit. So, and then I guess like probably the region in the middle would behave like flat space in the end, but question is how to kind of localize observable there.
Yeah. So it's a little bit like the analog of what we were seeing in the zero brane case, right? Where you have this patch of flat n theory middle. But there presumably is such a patch which emerges on the 2B side, right?
Right. That's certainly true, yes.
Let's see. Okay, thank you.
One question, Shota. So when you write down this gravitational solution, that there was a previous analysis by UCLA people and other about this solutions which preserve this symmetric F4. Presumably the real form was SO 5,2 or 6,1.
Yes. Yeah, 5,2. Yes.
There, I guess the solution would have ADS 6 times S2.
Exactly.
And then the geometry would look like what you have drawn there times S2 times ADS 6, where things are shrinking, where the S6 is shrinking, ADS 6 will shrink. Or how does that?
So in their case, like if you say that ADS 6 shrinks, then it's a bit singular geometry. So if I remember correctly, like in their geometry, only S2 shrinks. So like their geometry only have like a blue lines basically. So the global structure is different.
I see. So also, I mean, it's a bit confusing that one can go from ADS 6 to S6 with a simple, just by changing that signature there. Because, for example, when you have negatively curved and positively curved, they balance each other out, right? ADS 5 times S5, type 2B has ADS 5 times S5 solution, but not S5 times S5, right? So I wonder how this works out exactly.
Right. So yes. Right. So this is a little bit subtle point. For example, like if you look at this, like the instanton geometry people study in the past, like you can already see that things are actually complex, right? Like this is supposed to be some. Sorry, maybe you don't see it here. So you don't see it here, but like the action is actually dilaton actions is generally complex here, and So because we are talking about Euclidean ADS, Euclidean type 2B, so certain fields become complex. And yeah, so I guess that's probably one answer to your question. And then there are certain conditions of like what kind of, what's the reality condition one should impose for the Euclidean type 2B geometry. So, and then like which is discussed also in this like the instanton geometry as well. And we basically followed that criterion and imposed that condition here. But
so this is like actually working with S5 times S5 with some understanding of the analytic continuation.
Right. Yeah, I think that's the case. Yeah.
Is it sorry? Please excuse me for interrupting. Then is it like some of the fluxes are imaginary? Is that what you meant? Like
no, the fluxes are actually real.
Okay.
But like a certain fields, like the fields value are, I think, complex. Yes, certain field values are complex.
Okay.
So I think that's the condition people normally impose in this like a Euclidean supergravity. You still impose that the fluxes are real. But,
okay.
Yeah.
But a geometry such as S5 times S5 would need to have some cosmological constant to support. No?
Right. So okay. So yeah. So I think So in that sense, probably like it's slightly. Let me think. Yeah. Yeah. So it's probably slightly better than just analytically continuing S5 times S5 to S5 times S5. But honestly, we don't have I don't have a sharp answer. I don't have an actually deep understanding of this like a Euclidean Euclidean condition for the type 2B supergravity. So it still confuses me. So
thank you. More questions? If not, let's thank Shota for a wonderful talk.
Thank you very much.
Thank you, Shota.
Bye.
Okay, thank you.
Bye.
All right, bye.